Bismillah ar-Rahman ar-Rahim. Today, inshallah, on our first video on the lecture series of course ISE 205, we're going to be talking about chapter 6. Title of the chapter is Descriptive Statistics. Well, what are we expecting to learn from this chapter? Well, we are expected to describe sets of data visually, as it shows here in the outline of the chapter. We have various methods that we're going to learn. But before, we need to introduce some essential concepts and terminologies that are going to help us throughout this chapter and coming chapters and also coming courses. So, to begin with, let's explain what data is. Well, these are the things we're going to be dealing with most of the time. These are the numbers that we're going to conduct the studies, finding the averages, variances, and making the graphs from. So what are they? They are just numeric observations of a phenomena of interest. Numeric, just numbers. It's not complicated, but just for clarifications, sometimes maybe you're taking a machine learning course or AI course. In this context, data can be more than just numbers. It can be, for example, pictures, can be voices, can be various things. But for the intended purpose of this course exactly, we're gonna just deal with numbers. So that's it. Well, we have also a sample and what a population is. So what is a sample and what is a population? A sample is common, is known. A sample is just a part of something bigger. Does this make the population that something big, that the entirety of it? Yes, indeed. In this context, the population is the entirety of all possible observations, while the sample is just a part of that, of these observations. Just we are using them for analysis. So according to the definition of the book, a sample is a portion used for analysis, just a part of something bigger. Well, while a population is the totality of all possible observations. Well, let's have a little bit more talk. But first, let's see a visual representation of population, the sample, just straightforward. And a population is all possible observations. Let's have a point of discussion here. Well, we know that the more the data is, the more accurate our results are. Of course, having a bigger sample and a bigger amount of data can yield better results, usually, generally speaking. So why don't we take populations? Why do we need to deal with this concept of a sample? Because sometimes taking populations is quite unrealistic and counterproductive. Let's take an example for this. Let's say that you are in a factory and you want to conduct a study on a property that a product of you have. Let's say, for example, you have a product, you have a phone, and you want to test how water resistant is this phone. So if you want to test such a thing, you might need to destroy this phone. So if we're taking a sample from your stock, let's say you have 1,000 of stock and we're taking a sample of 25, for example. We're destroying these phones, we're seeing how much they can survive in water, and that's it. We're getting good numbers that will give us a good estimation on the rest of the units we have of this exact product. However, if you're using the entire population of your product, you're not going to end up with anything. You're going to use the entire thing into the study. You're going to destroy everything and you're not going to get any use of it. So that's why that's a reason why we take samples instead of populations. Another example might be it's just tiresome. Like if you're taking a population of a certain nation, maybe Saudi Arabia, you wanna conduct a study on the population of Saudi Arabia. It can be quite difficult to gather everyone. It's quite unrealistic. You're not going to get everyone. Some people are traveling, and for many excuses, you might not be able to find the population for it. So dealing with samples is way easier and way better. So at the beginning of the chapter, I said we're going to be describing sets of data visually. So we have this acronym to help us to know what to look for in a graph or in a visual representation of the data. This acronym is SOCS. S, the first S stands for shape, the O stands for outliers, and the center stands for the center, and the spread stands for the spread of the data and how dispersed your data is. We're going to go through each one of them. Well, the shape can tell you a lot about the graph. For example, let's take one of these shapes. Let's take this shape. This shape tells you that your data is leaning towards higher value. You can make of this fact whatever you want. Maybe you are looking at the grades of students, and the higher the grades are better. Or maybe you're seeing the count of death throughout the years. So this is going to be a traumatic increase. So you make of the shape of the data what you want. Sometimes you're not going to get a clear shape, like one of these famous ones, but if you got one of those, those have their properties, and we're going to talk about their properties, inshallah. Outliers. Let's talk about outliers. Outliers is extremely simple concepts. Just a point that is far away. As you can see, the majority of the points are here, while the outlier is just here. This can mess up with our data in some way, or maybe can tell you there is an anomaly in your process. You can make of the outliers what you want, but their presence tells you something, always tells you something, most of the time. Well, let's talk about the center. Well, the center is quite a straightforward concept. It's the center of the data. Well, if I tell you where is the center, you're going to point here. Here is the center. Well, you're correct. Here is indeed the center. Well, what does it tell us? Well, in a usually normally distributed data, the center is going to be where the majority of the points are. And we measure the center by the mean. What is the mean? The mean is what we know as the average, but we're going to call it in this course the mean. So if I say the mean, I mean the average. I'm not going to call it the average unless there is a reason or a purpose for calling it the average, but it's going to be usually the mean. Well, as we said, this in the normally distributed or in a normal distribution, you're going to find the mean where the majority of the data is, which can tell you something also about where most of your observations lie. We have also the spread, which is characterized in the narrow and the flatness of your graph. As we can see in the graph above, we have the majority of the data squeezed, as we can say, in a small tight area, while in the graph below, we can see the data dispersed throughout the graph. Well, we measure the spread by something called the variance. Well, what is this variance? Maybe it's a foreign concept for many, but the variance measures how far the data is from the mean, and we're going to talk more about this. But bear it in mind, the variance, in translating the word variance to Arabic, it means اختلاف أو تباين or something of this sort. So the more your اختلاف or your differences is, the more you have differences, the higher your variance, the more you're going to have the data spread and dispersed. But the lower the differences in your data, naturally you're going to have them in a tight area, more closer to each other. So this is it for this acronym. Well, let's talk about the mean. The mean, as I have mentioned, it is the average. Well, we have a sample mean, as we have seen, we have a sample and we have a population. So we're also going to be having a population mean. Let's talk about the sample mean first. The sample mean has the same formula that we know about the average, which is the sum of all values divided by the number of values. The sample mean is denoted by x bar, this letter here, the x that has a dash on top of it, we call it x bar, and it equals to the sum of all points, sum of all values you have in a data point divided by the number of the data points you have, or what we call the sample size. Well, for the population, it's quite similar. Population has the same formula. Don't worry about this one here. We're gonna be talking about it, inshallah, in chapter 3. But it's the same formula. You sum all the values you have in a population, then you divide them by the number of points you have in this population, denoted here as capital N, where the population mean is denoted as the Greek letter mu, as we see. Now let's talk about the variance. As we have seen in the mean, we had two cases, two formulas, one for the sample and one for the population. We're going to have the same thing for the variance. We're going to have a sample variance and we're going to have a population variance. So these are the formulas for both, and the sample variance is denoted by S square, where the population variance is denoted by sigma square. So let's talk about let's talk about the sample variance for a little bit here. As we've seen, it's denoted by S square, which equals to this argument here divided by the sample size subtracted by 1. Well, what does this argument here mean? Well, as we have talked about the spread of the data, the spread must be measured according to a point. Of course, you have to have a point of reference that you spread how far the data is from. You cannot just say the data is farther apart. No, you have to put a point of reference. And this point of reference was chosen to be the mean. So logically, if you want to see how far each point from the mean, you're going to get the distance. So this is exactly what's happening inside. You're having all of the data points, as is chosen here from the sigma, all of the data points subtracted by the mean to get the distance. So you're getting the distance of all the data points, squaring them and adding them all together. So this is exactly what's happening here. So it only makes sense that if your points are far from the mean, are getting just farther from the mean, that you're going to have a high variance because you're going to have a higher number. But if your data is close to the mean, you're going to have a low distance, which is going to give you a lower variance. And this bottom part is n minus 1. Here is the calculating difference between the sample mean and the population mean. Of course, there is a difference in notation, where S square is the sample variance and population variance is sigma square, and you have the x bar as the mean and mu as the mean. But this part is actually the calculating difference, where you have to subtract 1 from the sample size, and here in the population it's left alone. So bear in mind, if you are in an exam setting or a quiz and there are partials, most probably if you are asked to find the sample variance, this one, and you write this equation there, you're not going to get the partial. So bear in mind, keep the notation in your head and don't forget about it. Well, let's talk about another thing that's called standard deviation, which is quite important. Well, standard deviation is the square root of the variance. Why do we use the standard deviation? If it's just the square root of the variance, just use the variance. Like, why do we need to square root it to get a use out of it? Well, here is the catch. The variance has the units squared. So let's, for example, say that you are measuring the variance of the lengths of tables, for example. If you find the variance for your data set, your variance is not going to be in meters, which is the length. No, it's going to be in meters square. Not necessarily that it indicates that something about the space or the area, it's just that the unit was squared. So we cannot really make a good comparison. If you tell me, for example, that the tables are measured in meters and they are within a certain meter square away from each other, it doesn't really give a clear idea. So we want to make the variance or the measurement of how varied the data is measured in the same unit that the data is measured with. So we have the square root of the variance, and it gives us the standard deviation, which is most commonly used to find the actual dispersion of the data. As we can see here in the formula, it's just the square root. You take the square root, that's for the population, that's for the standard, that's for the sample. This is the population standard deviation, this is the sample standard deviation. So don't get them mixed. Same thing as the variance, just squared. So, okay. Here we have a computational formula for the variance. As we have seen, the previous formula was quite simple, not too hard, not too difficult, but it's a handful to solve equations with. Like, let's say, for example, you have about 30 data points and you have to plug in 30 arguments for subtraction in your calculator. It's going to be annoying, and you might get some mistakes. So these formulas here are way easier. Not way easier, but quite easier. You still need to do some work, but these are taking some load off. As we can see, we have two formulas. This formula, assuming that you have not found x bar. Well, here it's capital X bar, doesn't matter. It's just x bar, it's the mean. But majority of the questions you're going to be asked, like generally speaking, you're going to be asked to find the mean. Then in the other part of the question, you have to find the variance or the standard deviation. So using this one is most common and better usually. Variance and standard deviation for the data set. This one. Well, usually, what's the first thing you should do when you're presented with such a problem? The first thing you should do, you should identify what's your sample size, how many data points you have, or population size if we had a population, but here we have a sample, so it's a sample size. Well, if you count them, hopefully you're gonna get 10. So I forgot to write the n in the notes, so I'm gonna write it here. N equals 10. And also we are assuming that we have already found x bar, or x bar is easy to find. We don't need to do the calculation. We don't need to do the calculations here for it. So the x bar, if you sum all the values here and you divide them by the sample size 10, you're gonna get this number, hopefully. Now we have this formula. We almost have everything. We just have this argument, the sigma xi square. So how to solve for this argument? Well, this argument is extremely simple. You take each element in the data set, for example, this 11, you square it, and then you take the 3 and you square it, and you take this 2 and you square it, and you square each and every single element you have in the data set by itself, and then, only then you add them together. If you add them together and then square the sum that you got, you're gonna get a totally different result, a totally wrong number. So if we do the process correctly, we should get this number, 5,112. Now we just plug in numbers in the formula. So let me present it here, show it here. It wouldn't hurt. So according to the formula, we're gonna have 5,112 minus 10 multiplied by the x bar squared, which is 16.8 squared, divided by n minus 1. If we had a population, this argument would have been n, but it's a sample, so it's n minus 1. So we're gonna have it to be equal to 9. Ahlan wa sahlan. Well, if we solve and complete solving, we're gonna get that the variance is gonna equal this value, and if we have the square root of it, which is to find the standard deviation, we're gonna have this value here. And this is a problem for practice, and this is the answers for it if you'd like. Now let's talk about the range and the median. Well, both are simple concepts that we were introduced to in middle school and high school, but we're gonna be reintroduced to here. Well, the formula for the range is you take the highest value you have in the data set and you subtract the lowest value you have in the data set from it. A note worth mentioning regarding the range that we have two ranges. We have the population range and the sample range. And this population range is always either greater or equal to the sample range. Why? Because in your population, if you're taking a sample from your population, you might not include both the highest value in the population and the lowest value. You might take something from the middle. You might take something that has the highest value, not the lowest. You might take the highest and the lowest. And in this case, you're going to have them equal. But always, you're going to have the population range either greater or equal to the sample range. The median. Well, the median, as it's defined here, is the value that divides the data set into two equal halves. So we have the one highlighted with red here is the median, and the data is divided in half, where we have 2 to this side and 2 to the other side of this point. A question might arise. Well, we have the mean also. And this says that it divides the value in half, so it's going to be in the center. And we said that we measure the centrality of the data with the mean. So are they contradicting? No. Are they doing the same job? Not necessarily. Here is the catch. Well, the median divides the data in terms of the number of data points in regard of the sample size or the population size. But the mean divides the data in regard of the values. So depending on your values, your mean might be higher or lower, regardless of the number of data points you have. It just cares about the values. But the median care about how many values you have. So this is the difference between them. Well, let's talk now about our first way of describing data visually, which is the stem and leaf diagram. The stem and leaf diagram, as it's defined here, it's a plot where data is represented in two parts. The first part we call the stem, from stem and leaf diagram, which includes the first digit or digits. So the stem can take more than one value. However, the second part of it is called the leaf, which only takes one digit, strictly one digit. So what is the utility for the stem and leaf diagram? Why is it useful? Well, the stem and leaf diagram helps calculating the median and the mode by just looking at it. And it also shows the shape, outlier, clusters, spread, and centrality, our acronym if we remember. Well, let's see an examples for a stem and leaf diagram. Well, these both are two stem and leaf diagrams, and how to read them. Well, first of all, we have here our stems, as we said, that can take a digit or more than one digit. But here, our leaves, where you can only take one digit. Well, I can see more than one digit here. I can see plenty of numbers. Well, each one of these numbers represent a number, one number by itself. So this 0 and this 2, if you join them together, if you read them from the left, you have the stem to be 2 and this one to be 0. So we have 20 here. Well, let's go to the 3. We have the 3 as the stem, and we have the leaf to be 0, 2, and 5. Each one of these numbers is considered a number within the 30s. So we have 30 if we combine 3 and 0, and we have 32 if we combine 3 and 2, and 35 if we combine 3 and 5, and so on for the rest of the data. So this is how we can be able to read the stem and leaf diagram. And as we can see, the data is organized from the highest to the lowest. The leaves are organized from the lowest to the highest. Well, there are multiple ways on how you can write the stem and leaf diagram. Here we took an example for having a value in the tens and maybe in the hundreds, and you stick one number to it. We can even further divide the tens or the hundreds if we would like so. So for example, here this number 6L is the lower part of the 60s, where we have the values from 60 to 64 here. So how do we read these numbers? It's 6 and 1. This is 61, 63, and 64. And it goes for the rest. This is 6U, which is 6 upper, where it includes the values from 65 up to 69. And the same goes for the rest of the values here, upper and lower. And you can have even more divisions. And you also can include numbers with decimal in the stem and leaf diagram. It's quite versatile, and as you can see, you can kind of see a shape forming here. So yeah, it matches what we need in a graph. Now let's have an example for how to solve a stem and leaf diagram. Well, we are presented with this question: construct a stem and leaf diagram for the given data set and find the mode and the median and the range. Well, I think that I forgot to mention the mode. The mode is the most repeated value, which is in Arabic minwal. So the first step you do in constructing a stem and leaf diagram, and focus with me, you should make a straight line. Now we finished making a straight line. Now we can look at our data. Okay. Well, we can see where is the lowest and highest value we have in our data. Well, we have a 10 and we have a 105. Okay, good. Okay, how our data is behaving? Well, we can see that our data is kind of going through tens. Like we have 10 here, we have somewhere here, we have 20, we have 30 there, we have 40, 50. Well, we can construct the stems to include these values in the tens, and we put them here. So for example, we put the 1 representing 10, 11, 12, 13, 14 up to 19. We have the 2 representing 21 up to 22, and so on for the entirety of the data. So we're gonna end up with something that looks like this. Now we look at the values we have, we look at the stems that we have assigned, and we look at the things that matches these stems, and we take the last digits. We steal the last digits and we put it here. So the most obvious example here is the 10. So the 10 matches the stem of number 1. So we have to take the leaf of it and we put it here. Another example might be 13. Same thing goes into the 10 also, the first row here, and we put the 3 here. But bear in mind that we need to arrange them in an ascending order. So we get to the lowest values first, then we go up to the highest values then. So if we put the 3 here, and then you get a 10 here, yeah, well, you might want to push the 3 to put the 0 here again. And you do this for the entirety of the data. Maybe we have a 4 here. So how can we solve the 4? Well, we have 45. We put 5 here. Oh, but we have a 40. Okay, so we put the 0 first, and then we put the 5. Do we have any else within the? We have 43. So we have to put push the 5, and we put the 3, and you get the idea. Extremely simple. We're gonna end up with something that looks like this, and it kind of represents a shape where the majority of the data points going towards the lower values. So it represents some sort of a shape, kind of useful. Now let's solve the questions that we have here. How can we find the mode, median, and range? Well, let's put this number here to begin with, the sample size, because we might need it, and we're gonna need it indeed. Well, the mode is the most repeated value. As we can see here, we can easily see that the most repeated value here is 10 and 13. So let's go. What about the median? Okay, the mode was relatively easy. Now let's find the median. Well, the median is the value in the middle, and we know that we have 18 data points. So if we would go to the middle gonna be between 9 and 10, something between them. And we know if we had 2 values in the middle, we have to add them together, subtract them by 2. So now we can just count until we reach 9 and 10. So counting from up, not from down. I tried to count from down and I didn't get the same value. So count from up. Now let's count. As we have said, we have 18 data points. So the values gonna be in the middle are the 9 and the 10. So let's count until the 9 and the 10 value. So we have 6 here, we have 7, 8, 9, and 10. So these 2 values are the ones in the middle, 40 and 43. So add them together, divide them by 2, you're gonna get 41.5. That's it for the median. Now at last, the range, you take the highest value and you subtract the lower value from it. So we know that the higher value is going to be here below where we intended, and the lowest value is going to be here, which is the 10. So subtract the 105 from the 10, you're going to get 95, and that's how we solve this question on the stem and leaf diagram. Now let's talk about quartiles. Quartiles are 3 values that divide our data into 3 equivalent parts. So what are these quartiles? Well, as we said, there are 3. We have first the lower quartile, or the first quartile. Second, we have what we call the median, and what we know as the median is also considered a quartile, which is the second quartile in this case. And we have the upper quartile, which is the third and last one. So what are the properties of these quartiles? Well, where the lower quartile has 25% of the data below it. So if you have a data, this quartile, the value at which the first quartile lay, gonna have 25% of the data pushed behind it, while 75%, the rest, are gonna be above it. Well, and we can find its location or index by this formula here. And we're gonna go further, and we're gonna know how to use it, and we're gonna find the quartiles. In an example, in a practice example. Well, now the median, we know what the median is. It has 50% of the data below it and above it, but it also has a formula of how can you find it, by adding 1 adding 1 to the sample size and dividing by 50 over 100, or half. I'm doing these fractions like this because we're gonna be introduced to something also called percentiles, where we're gonna have 100 here. So getting familiar to this shape is, in my opinion, way better. Now talking about the upper quartile, this one had 25% below it, this had 50% below it. Naturally, this is gonna have 75% of the data below it. And also it has a formula to find the index of it, which is this one. As we can see some sort of a pattern here. It's not complex, it's extremely easy. Now let's go to an example. Oh, here is I forgot this image. Well, here it's represented where we have the one in light blue to be the lower quartile, the median highlighted in red, and the upper quartile in green. We see 25% behind, 50% behind, 75% behind. Now let's go to the practice. Well, we are represented with this data set. So if we are trying to find quartiles, the first thing you should do is order. The first thing always to order them. You cannot find the quartiles or the median or the percentiles, anything. You cannot find these things with the data jumbled like this. You have to order them ascendingly, from the lowest to the highest. Now, identify what's your sample size or population size, needless to say. Identify the size of your data set, which is 13 in this case. Now, let's find the first quartile, and we're gonna find also the second, and we're gonna find the third. So finding the first quartile, we have to find where it is first before we find the value. So the location of the third quartile at 3.5. So what does this mean? The first quartile is at the index 3.5. So we have to count 1, 2, 3.5. So it is here. It's between 13 and 18. So we know it is 13 point, or we don't know it's 13 point something, but we know it is between here, somewhere between here. So what should we do? We take the first value, which is the 3, the third index here, and we add it to the distance, the half. We said it's between the 13 and the 18, within the measurement of the half of the distance. So we take half of the distance, or simply you subtract the fourth here, the 18, the fourth index by the third index, you get the distance, and then you multiply it by this fraction. Always by this fraction, okay? By the fraction you have in the location index. And then you get the value 15.5. Now the second quartile, we know how to find the second quartile. It's needless to say. You find the location, and lucky for us, our data does not give us fraction in the index, so we straightforward go to the index number 7. So we have to count 1, 2, 3, 4, 5, 6, 7. 24 is indeed our second quartile, which is also called the median. Now the third quartile, well, the third quartile is in the position 10.5. So it is at 10, and then you get from the 10th index, you get half of the distance. And then here you get the third quartile. So let's count. We have 13, so we can count from here easier. 13, 12, 11, and 10. So our 10th index is 43. Okay, but we don't want 43. We want the distance in the middle between the 43 and the one after it, which is the 46. So we do the same what we did. First of all, we lay the 10th index. We just put it here, and then we add to it the difference between the 11th and the 10th, the distance between them, which is, in this case, I think it's going to be 3, multiplied by 0.5, we're going to get 1.5, and adding 1.5 to 43, you're going to give us 44.5. Now, more practice does not hurt. This is an example for you to solve. First of all, you have to order this data, and then you're going to be able to find these quartiles. These are the answers. If you got the same answers, then you're doing good. If you're not, keep practicing. You're going to get better. It's extremely easy, these quartile things. Now, let's talk about percentile. Kind of the twin brother for the quartile, but it's an older brother. You know, it has more variety and more things to talk about. Well, percentiles are values that has k% of the data below it. We're going to explain what that means. And also the quartiles we had has percentiles in them. So the first quartile is the 25th percentile, which is denoted by P25, and the second quartile, which is the median, is denoted as being the 50th percentile, and the third is being denoted as being the 75th percentile. Well, this is the formula of how can you find the location of any percentile you want. So here we said the percentiles has k% of the values below them. This is the k that I meant. So if you want the point in your data that has 20% of the data below it, you substitute here by 20 and you get the location. Of course, if you have the data point and the rest of the thing. If you want, for example, the 43rd percentile, you just plug in here 43 and you're gonna get 43% of the data. You're gonna get the value that has 43% of the data below it, and so on for the rest of the numbers. Even you can go to fractions also. So yeah, that's it. Now let's have a practice on percentiles. The question says, find the listed percentiles for the data set given below. So as we know, as we have seen in quartiles, we had first to order the data set we have. Same thing goes for percentiles. We have to first order them. So we order them ascendingly, and we have to know how many data points we have. And the number of data points, if we count them, hopefully you're gonna get 12. Now, let's find the 20th percentile and the 60th. The 20th percentile, we've seen the formula. The formula said k over 100 multiplied by n plus 1 if we want to find the location. So the first thing you have to do, find the location, then find the value. First the location and the value, both for the quartiles and percentiles. So for the percentile at 20, we have to find the location, and the location is noted by the formula 20 over 100 multiplied by n plus 1, which is 12 plus 1, which is 13. So if we do this equation here, we're going to get 2.6. Well, some cases you might get lucky. You might get 2 instead of 2.6. You might get just a number by itself without a fraction, without a decimal place. Here you got lucky, because if you got 2, you just know that the location of the 20th percentile in this case is going to be at the index number 2, just number 4. That's it, the second number. But unfortunately we didn't get lucky, so we have to deal with this fraction. So we know that 4 is there somewhere. So we know 4 that we're going to use 4. So to begin with, we put 4 here. Then we get the distance between the 3 and the 4, because we want to get the 0.6 of it. We get the distance, so we subtract them with each other, and we multiply them by 0.6. We get the value of the 20th percentile, which is 9.4. So 9.4 has 20% of the data below it, and 80% of the data above it. Now let's solve for this one, for the 60th percentile. Now, unfortunately here I got the numbers wrong. I just copied it. I did not put the numbers, but the value here is true. I'm gonna write the correct thing on the board, don't worry. So first we have to find the location, which is 60 over 100, as we've seen in the formula for the location, multiplied by the the sample size plus 1. We're gonna get 7.8. So now 7.8, we know it's 7, the 7th index has something to do with it. So we have to put the 7th index. If I would write it on the board, where is the 7th index? So that's 1, 2, 3, 4, 5, 6, 7. So the 7th index has something to do with it. So we write the 7th index, which is 24. Now, it's not 7th index alone, it has a 0.8 here. So what should we do? We get the distance between the 7th and the 8th index. So we do something like this. We take the 8th index, 28, we subtract it from the 7th index so we can get the distance between them. Then we multiply them by this fraction, which is 0.8. And if we do this, this is the correct, this should be in place of this. So if we do it correctly and we calculate it, we're gonna get, inshallah, 27.2. These are percentiles that you can practice by yourself, and that's it for percentiles. Now, let's talk about something called interquartile range, which is denoted here by IQR. Interquartile range is when you subtract the 3rd quartile and the 1st quartile. What's the use of this? Well, the use of this that it has 50% of the data in it. So if we take the 3rd quartile, which is somewhere here, and the 1st quartile, this place here gonna have 50% of the data naturally, because below this one is 25%, which is the first quartile, and above this one, which is the third quartile, 25%. So in the middle must be 50%. So this might be beneficial to know. And also we're going to use the interquartile range, IQR, into finding the into constructing a box whisker plot. Now let's talk about frequency distributions. Frequency distributions are compact summaries of data expressed as tables, graphs, or functions. I wrote here tables, it should be distributions, but anyway. Here are examples for them. Here is a frequency distribution as a table, and here it's as a graph. Well, we call this a frequency distribution table, naturally, and this is, we know as a histogram. Well, we know what a histogram is, we took it before, but let's talk a little bit more about the frequency table, and let's learn how to read it. Well, the frequency table has something called classes, which are these intervals at which you can divide the data into, and each class and the number of classes and how big the class, as we can see here, the class are going from 70 to 90, 90 to 10, so it's a width of 20. So the number of classes, the width of the class, all depends on your data. The data you have will determine the number of classes and how big the class is. We have here 20, and we have the range here to go from 70 to 250, which is maybe around 180 of range. So all of these going to be determined by your data, and it's different for each data, and we're going to learn, inshallah, how we can construct one. Well, here is the frequency, which denotes the number of data that fits this class. So maybe in our data, I don't know, maybe we have 71 and 82 only. These are the two only points that can fit here, so we have frequency of 2. And the same goes for the rest. We have something called the relative frequency. What is relative frequency? It's the percentage of the occurrence of each class in accordance to the rest of the classes you have. In simple terminologies, you take the frequency, you divide it by the rest, the number of your data you have. That's it. That's how you get the relative frequency. So 2 over 80, you're going to get this number. 14 over 80, you're going to get this number, and so on. And naturally, if you add all of these together, you're going to get 1. So, for example, if we got in our major exam, we got a frequency table. So when we got to know that whether you messed up your frequency table, you can sum all of these values, and if they don't add to 1, maybe they are less, maybe they are more, then you definitely has a mistake. Well, the cumulative relative frequency. The cumulative relative frequency is you take, first of all, in the first element or first class, you just get it's the same as the relative frequency. But the more you go, it changes, because it's cumulative. So cumulative, you adding on top, you just keep summing, adding. So here in the second one, we got originally in the relative frequency, it's 0.0375, but here it's 0.06. Why? Because we added the one above. So the relative frequency, you take the frequency, you add it with the ones above it, all of the ones above it. So for example, if you want the relative frequency for this class here, we have to get this one, we add it with the one above it, and the one above it, until the last one above it, and then we get this number, 0.8, and so on. So naturally, if the cumulative relative frequency for the last class must be always equal 1. If it was less, wrong. If it was more, definitely wrong. So how to construct a frequency table? Well, first of all, we have things into consideration, because it has 2 steps, in my opinion. One is initializing and the last one is finalizing, where in the initializing stage, you have to see the numbers that you might need to tweak to get the desired values that you want. We're going to see more in the example. We're going to have an example, inshallah, for this. Well, the consideration, you have to first find the range, find the echelon number of classes, and find the class width. The range has this formula, as we know. Well, the number of classes is square root of n. It gives you a good idea on how it is. And the number of classes is this one here. You see, as we have, that's a class, and this is, okay. This is a class, and this is a class, and this, until you count all of these, maybe they sum to around 9, maybe 9 classes. 1, 2, 3, 4, 5, 6, 7, 8, 9 classes. So this is the number of classes. How we can get it or get a good idea about it? We take the number of data points we have, and we take the square root, and it gives us kind of an image about it, where it might be. About finding the initial class width, you just have to find the range first, and you divide it by the initial number of classes, and you get the initial class width. However, in the finalizing stage, you have to have finished determining the number of classes, either you have rounded up or down, and determine the class width with the same method, and determine a starting point. So let's see an example of how can we construct this frequency table here. Well, worth mentioning that the data at which this table was constructed is from the book at table 6.2. So if you want to see the data that they used to construct this table, you can go look at it in the book in table 6.2. But let's get into the question. The question says, construct a frequency table for the data in table 6.2, the one in the book. Well, first we have our consideration, the initializing stage, where we have to find the range, initial number of classes, and initial width. So for the range, if we look at the table in the book that we used to make this one, we're going to see the highest value to be 245 and the lowest to be 76. That's our range. Initial number of classes, taking the square root of n, of course, from the table, and we get this value. For the initial class width, as we said, we divide the range by the initial number of classes, we get this one. Here is the thing. We now can see where the rounding up or rounding down takes place. Because this, if you look at it, can be rounded up to about 9, and this one can be 20, which definitely gonna make for a better class width, because as we can see here, the class width that was used here is 20, and it gives us a better representation. So we can see the interval is from 70 to 90, from 90 to 110, while if we would have relied on the original one, we're gonna have 18.9, which is kind of ridiculous to work with and kind of annoying. So we had to round it up to make it more suitable. And also this original ones might not give us the shape that we want. So rounding up sometimes is a good idea. Well, usually is a good idea, especially if you have these numbers. You're not going to get complicated the frequency tables or histograms. You're gonna get simple stuff that is obvious what you have to do, and how can you tweak it. In the finalizing stage, we've seen that we can round this up. We rounded it. The class width, also we rounded it closer to 20, which is a better number in my opinion. And we found the new range, which is 180. Well, this new range allows for something. Well, it allows for us to change our starting and ending point, because originally our range was 169. So because of our values, we had the highest value to be this and the lowest value to be this one. But now we can change our highest and lowest value depending on the range we have. So we can start from 70, starting point at 70, and end at 250, and we still gonna have this exact same range. So if we add the starting point to the range, we're gonna have the last and final value that includes all of the values we're gonna have in the frequency table distribution. And with this, you can construct a histogram, the exact same one we have seen in the slides earlier. This one on the right. This one is constructed from the same data that used to construct the frequency table. So we have seen histograms before. We know what histograms are. So let's have a definition and let's see the ways we can use histograms Well, a definition for histograms can be, a histogram is a visual display of a frequency distribution similar to a bar chart or a stem leaf diagram. So the stem leaf diagram we took also can be considered as a frequency distributions. Here are some examples for a histogram. Of course, we've seen couples since we started the lecture. What are they useful for actually? Well, their utility is, first of all, they're reliable in visualizing larger data sets between 75 and 100. You can go more, you can go a little bit less, but usually speaking, this number of data points or this sample size or population size is suitable for histograms. Also, it shows the SOCS, the acronym we had, that stands for the shape, outliers, and center and spread. Now, let's see how can we construct a histogram. Well, we have seen the frequency table, the one that we have gone through tiring work to construct. So it should help us in constructing a histogram, but do we need all of it? As we can see, by the way, this table is what you would, this is the histogram that you would expect to result from this table. So how can it help us in constructing that histogram there? Do we need the entirety of it? Actually, no, we don't need all of it. We just need this part. If we are willing to construct a histogram that would take into consideration in the y-axis or in the second axis the frequency instead of the relative frequency, you could be asked to find the relative frequency. In this case, you have to find the relative frequency in the table. But usually speaking, unless it is specified that you need to construct a histogram according to its relative or cumulative relative frequencies, then you are most probably, like all of the time, let's say, that you are required to just the frequency as it's chosen here. So this two-part, as it shows here, it is all what we need to construct a histogram. As we can see, here are the classes which are characterized in the columns that we see. So the first class we have is from 70 to 90 here, from 70 to 90, and this is the column we have. As we can see, where is the frequency, the class that has the most frequency in it, we can see it's 150 to 170. So if we go to our data, 150 and 170, this column indeed has the highest frequency. Extremely simple. Now let's talk about the shape of a histogram. At the beginning of the chapter, when we discussed the acronym, the SOCS, I was talking about the shapes, and shapes can tell you things about the data, and this is a thing that you have to look for. But I did not speak thoroughly about what indicators the shape might give you. Now we're gonna discuss it, inshallah. The shape of the data can tell you, first of all, can tell you the behavior of the data, as simple as this. If you see the majority of your data is leaning toward higher values, this is something to be noticed. And if you see them leaning toward lower values, this is also something to be noticed. And as much as they both are noticed, the symmetric one should be noticed. Of course, if you're, for example, if you're a teacher, if you're a doctor, if you're a lecturer, and you're giving a quiz or an exam, and you see that the majority of the grades or the marks of your students are leaning toward the lower values, that's something to be noticed, and your students are not necessarily doing well in their exams, and maybe they're not comprehending the material well. So these are things you have to look for, the shape of the data. So, and also they can tell us something about where the mean, the median, and the mode are in your data. So at the beginning, I showed you three shapes that now we're going to discuss more thoroughly. The symmetric, the one that has the majority of the lower, has a majority of lower values and a majority of higher values. This one we call, the one that has more lower values, we call it right skewed or positive skewed. And the one that has a majority of higher values is called the left skewed or negative skewed, as it shows here in the names. And this one is self-explanatory, it's symmetric. The right side is equal to the left side. Now, how can we know where the mean and the median and the mode in these shapes, or how can we get an idea where they might be located? Well, the picture here is extremely clear and self-explanatory, but I'm going to talk over it a little bit. Well, in the symmetric case, if you have a perfectly symmetric shape, which is quite unrealistic if we come to real-life applications, you're going to have the mean and the median and the mode to be exactly the same point. However, as we know, it's quite unrealistic. So maybe in a more realistic scenario, you're going to have them extremely close to each other. As much as your shape is symmetric, the closer they are going to be. In the right skewed, where the majority of the points are leaning toward lesser values, we have this shape we have the arrangement of these properties to go as follows: the mode, then the median, then the mean. I have arranged them here: mean, median, mode. So you can read them as you go up. The same case go here. As you go up, you can read median, mean, median, and mode. And here also mean, median, and mode. So you're going up. You have it. You should have it in your head in this arrangement: mean, median, and mode. And depending on where it goes up, you should start counting. This can give you maybe if you don't want to plot, maybe you don't want to plot your data, but you want to have a good idea where the majority of your data is. So this might be able to help you. So for example, if you see your mean is a lower value than your median, then you can say, okay, there is a good indicator that I might have a left skewed shape in this case, and so on. Same goes for the right skewed, and same goes also for the symmetric. Histograms are quite versatile. They don't only deal with numeric data as we have seen, but also they deal with non-numeric data, what we call categorical. And we have two types of categorical data. First one is called ordinal, and the second one is called nominal. Well, what is ordinal and what is nominal? Ordinal are data that has a natural order. We have here examples like years, military rank, days of the week. And nominal data that does not necessarily have a natural order, like genders, like colors, like furnitures, like whatever it is that does not have a natural order and not necessarily a number that measures something. Also, bear in mind, if you want to construct a histogram for categorical data, each column each category or each column has to have an equal width. So you don't need to do the range and all of the things we did for the numeric data that we have done already in constructing a histogram. You just get the frequencies and you plot it right away. Also, we have a special case of categorical histograms, or histograms that describes categorical data. We have something called Pareto chart. A Pareto chart is a histogram where categories are arranged in a descending order from the highest frequency to the lowest frequency. We have examples for it here. As we can see the Pareto chart, we have the highest, the column, the class, the category with the highest frequency first, then the second frequency to be the second, and so on. Same thing goes here. Don't worry about this line. I just found the picture on Google and had the line in it, so. Here is a catch though. We can see that we have numbers here. And we said that the categorical data are not numbers. Well, here is the thing. These numbers are not necessarily a measurement for something. They're just merely the name. As we can see here, they are airplane model. So it's just the name of the airplane. Like the room I am in right now. The room is room 1015 in building 59. It's not necessarily a measurement, it's just the name of the room and the name of the building, building 59. So you can have numbers in your categorical data as long as it's just a label. It's not really a measurement of something of that sort. Now let's introduce a new graph, the box and whisker plot. What is it? Well, a box plot is a graphical display showing its center, spread, shape, and outliers of the data. This is our 4-letter acronym, the one we got at the beginning. So what other utilities it might have aside from the acronym? Well, it shows you something called the 5-number summary, which are 5 important statistical numbers that helps you get an idea about the graph and what's your minimum value, what's your highest value, where the majority of your values lie. So here is a box plot with the 5-number summary, which you can directly look at the graph and get exactly where each value of this 5-number summary is. So you have the lowest value, the min, you have the first quartile, you have the median, the third quartile, and also the highest value, which is the max. You can directly just look at the plot and get where each and every one of these values lay. Now, let's talk a little bit more about it. Let's see how it's constructed. Well, to begin with, it starts with an axis, a horizontal or vertical, doesn't matter, but I'm gonna do it on a horizontal axis here. And then you identify where your first quartile and your third quartile gonna be. And based on these two, you're gonna have your box. Recall that I have said that the range where you have your first and third quartile has 50% of the data. So this is true for this shape here. You have 50% of the data inside of this box. Now, what do we add? We can add the median, which is this line here. So this line, the value at which this line lay is your median, the value that is in the middle of your data. It might be strange that it's not in the middle, but some data is skewed, as we have seen in the histogram example. So this might be a skewed data. That's why the median is a little bit going towards the left. Now this area, this first area we call it the interquartile range, or the box area, where we have the box. Do we have more areas? Of course, we have seen horizontal lines sticking out of this box, and it's called box and whisker. So where exactly shall we place the whiskers in this box? Well, we have also a region for them, and we calculate this region with this distance. So from your third quartile, you can move 1.5 IQR. And then this is going to be your whisker region, where you're going to be placing your whiskers here. And in the case of the lower bound, you subtract this value, which is 1.5 IQR, from Q1, and you get your lower whisker bound. So here are the whiskers, and they don't need to be symmetric. So they're just there. Also, we have another area too, because the whisker does not go forever. We have a bound for them. So what if we have a point that is outside of this place? We also have a region for them by the exact same process. We get this bound, and we subtract in the lower of the lower bound, we subtract 1.5 IQR, and we get the outlier bound. And we do the same thing, but instead of subtracting, we add it to the upper bound, and we get the outlier bound, where we have outliers, the points that are not involved in the whiskers. Also, we can do it again, and we get the extreme outlier bound, where you might have some points here that are far away from your data, and we are consider them extreme outliers by the same exact process all throughout. Now let's take an example. Now, of course, we have the 5 number summaries now. This is the lowest value we have, Q1, the median, Q3, and our highest value. Now let's take an example. How to construct a box plot? Well, first of all, I see it as a two-step process. The first step, we have our calculations, the numbers that we have to get ready before we start building our box plot. And the second process is when we actually get in with the ruler and start drawing the box. So in the first stage, where we have the calculations, first thing we have to find is the 5 number summary, and then we have to find the interquartile range, and then we have to find our upper bound by using this formula here, and we have to also find our lower bound by using this formula here. After we finish all of these things, we get to the drawing. Well, in the drawing, as we have seen, the first thing we started with is drawing the axis. After that, we went to drawing the box, and after it, we went to drawing the whiskers, and at the end, we identify where our outliers are and our extreme outliers, and we put them there, and we denote them with an arrow also. So, let's get into practice. Box plot. The question says, construct a box plot for the given data. So we have this data, and we want to make a box plot for it. So what's the first thing we do? Well, we know if we want to find the first quartile or the second or the median, we have to order the data. So the same thing applies here. First of all, we should order our data. So after we have it ordered, now we can find our 5 number summary according to our steps. First thing, 5 number summary. So, we find our 5 number summary. The lowest value is the 6. The median is in the middle, 14. Our highest value is 21. And our quartiles, the first quartile and the third quartile, as we have seen how to find them. Also, we have the interquartile range measurements. First of all, the IQR itself, and then we multiply it with 1.5, so we can use it into finding the boundaries for the whisker, for the outliers, for the extreme outliers. So now let's start drawing. First thing, as I said, we just have to make an axis. Then we take our Q1 and Q3 and we put them there. So now we're done with this. The first initial thing we are done with. Now what should we do? Now we have to find the rest of the bounds. So we just need, so when we finish this stage, we just look at the data and we just put numbers there. So how do we find our the rest of our bounds? As we have seen in the formula, we can find them by, we can find the lower bound by taking Q1 and we subtract this value from it. So where is our Q1? It's this one. And we subtract this value from it, we're gonna get 7.5. We have the 7.5 now. Let's subtract this value from it again. So we're gonna get this value here. So now if we would look at it initially, the books should be here because this is our first quartile and third quartile should be here, and our whiskers should be here, and our outliers should be here, and our extreme outliers should be here. So everything is arranged and everything looks neat. Now let's continue. We've done the lower bound. Now let's do the upper one. So the upper one would go with the same process, but now we're gonna take Q3 and we add it to this value. So the first time you add it, you're gonna get 19.5. The second time you add 19.5 to this value, you're gonna get 24. And now you have everything you need to draw the box plot easily. So first you draw the box. You identify where the median is. It's gonna be there because our median is 14 and it's leaning more towards the 15. Now, how to do the whiskers? As we see, we have bounds for the whiskers. So we cannot take just the lowest value, the 6, and we put a whisker from here to 6. We have an identified range for where we can put the whisker. So the lowest value according to the lower bound whisker, the lowest value that fits in this range should be where the whisker should be. And the lowest value that fits here is 11 because 6 is out, 6 in the outlier region. So we should use 11 to put our whisker. So our whisker, I've done the upper one first. Well, the same thing goes for the upper one. The highest value we have is 19. So it's leaning more towards 19.5 than it's from here. So it's going to be somewhere there. Not accurately. I've done it manually, so it's not, accurate or something like this, but it gives a really good idea, inshallah. Now we put our lower whisker. It's, it's 11, so it's leaning more towards this, this region. Now we put our outliers. And do we have extreme outliers here? No, we don't. So we just have outliers. Now you just identify your outliers. So because maybe you are in a quiz setting or an exam setting, if you don't identify your outliers, you might not get the marks for them. So make sure you put an arrow toward them. Maybe write the value if you want to be extra sure. So this is it for the box plot, and inshallah it was sufficient enough. I know it's a handful, but hopefully it was clear. Now here are some other plots that at least you need to know. So the first one is the time sequence plot. Well, the PowerPoint is not going accordingly. Well, we have also the digidot and we have the scatter diagram. So the time sequence plot looks like this. So what's the use of it? It shows values in a vertical axis. Well, we have our values here. It says sales, and we have time in the horizontal axis. Now we have here time in years. So it helps in showing trends or cycles over time. So as we can see here, the years are divided into 4 sections. The quarters as we know them, and at each quarter you can see there is some sort of a relationship that goes. So in the first quarter it trends up maybe, then it goes down until it goes the first quarter, then it goes up and goes down and so on. So it helps you find the relationship in accordance to time. Digidot plot. Digidot plot is just a time sequence plot or a time series plot with a stem and leaf diagram. As we can see, it's just combined stem and leaf diagram with a time series plot. So each point on a stem and leaf diagram, according to the time that you have identified this point, you put a dot here, and the points that on the left have been identified before the points on the right, and so on. Scatter diagram is extremely easy diagram. We always take it. We'll also take it in physics. It needs no explanation. But it shows, and we use it also in physics for this exact same reason. It shows correlation between in a multivariate analysis. If we use a scatter matrix, so we have something called a scatter matrix, where we put more than one scatter diagram on top of each other, so we can see relationships between variables, more than one variable at the same time. We're going to have an example for this. So let's have an example of matrix of scatter diagrams and talk about correlation. So here is an example of a matrix of scatter diagrams. As we can see here, we have 5 variables at the same time plotted, and we can see the relationship between each and every variable against the other. So instead of having about 10 individual scatter diagrams just thrown around, you can have them in this shape, and you can easily get access to whatever variable you want to plot against the other variable. And as we can see here a strong relationship between the color density and color, a strong positive correlation, as we might say. What is correlation? Well, the correlation coefficient is a number between -1 and 1. That shows the relation between 2 variables, and it's denoted by Rxy. Here is the formula for it. So let's talk about the correlation. The Pearson's correlation coefficient, the one that is the exact one, the one that between -1 and 1. Here is a good illustration of correlation, and here is a graphical representation of what correlation might do to your data. So at the center of it, we have 0, which means no correlation. If you go toward the right, your correlation gonna increase, and if you go toward the left, your correlation also gonna increase. But if you go toward the right, it's gonna increase in a positive way, as we can see here. So the more you increase your variable, the more the other variable is gonna increase. So the more you increase your x, for example, your y gonna increase. But it varies. Not every correlation is the same. We have weak and strong ones. So in the strong one, as we can see, the data is close to each other. So you can say with a good amount of certainty that if you increase x, y is going to increase. Well, in this case, you might get a significant increase if you increase x, and y going to increase significantly. You might not, as we can see here. So this value at the beginning is kind of higher than this value at the end, and so on. But there is somewhat of a correlation, we can say. Also, there is a negative correlation, as I've said. If you go towards the left, you're still gonna increase your correlation. So if you go toward the left, you're gonna increase your negative correlation. So when you increase x or increase y, the other variable gonna decrease. So it's like the proportional relationship or something. I forgot their names. But as it demonstrated here, the more you increase x, for example, y decreases. And here also shows, but here is a weak one. So we have strong and we have weak. It varies, as it shows here. This illustrates it well. So as you can see, between 0 and 4, there you can say there is no correlation, or there is extremely weak correlation. Or from 0 to 4, from 0.4 to 0.6, there is some correlation. And as you go more, you have stronger and stronger correlation, and 1 is the highest number you can get. So there is extreme correlation between them. If you increase x, y must increase. Also, correlation is not necessarily linear. You might have quadratic correlation. So this looks more like the shape of the x square or x raised to power 4 or x raised to power 6 function. You know, the parabola function, the parabola. So also this, you might have correlations that are not linear. Maybe you have a correlation that looks like the x cubed function, whatever you might want. But it also considers to have a probability plot. Let's talk about it briefly, because I have to leave now. Well, probability plot shows whether your data is normally distributed, and well, if your data lies somewhere close to this line, or on the line, preferably, your data is most likely normally distributed. But if it's like this, it's not. It's nowhere normally distributed. And normal distribution is extremely important. One of the most important distributions that you're going to be learning about in this course. And it's going to be beneficial in more courses, as I'm taking 315 right now. The first 2 chapters of 315, the majority of the time you're just using normal distribution. So it's a very important one, and it's beneficial to know whether your data follows this distribution or not. So with this we conclude chapter 6. I wish things were clear, and الله يوفقكم في اختباراتكم وكوزاتكم وياجركم. كده خلاص قفلنا. هذا والله أعلم. في أمان الله.